I had it. I literally had it, and then it just kind of right off. I'm sorry. Okay.
Is it like a secant line?
Well, call it, well, if it is a secant line, what would we call it? A tangent line?
Hmm.
I do make it. But a good start there, we'll call it point A, point B. That line is what we call a secant line. A secant line is a line that passes through a curve at 2 points. This is great. What could a secant line tell us? Well, a secant line could give us the slope of a function. But our goal here is to find the instantaneous slope or the rate of change at a single point. Well, the issue with the secant line is that it's not going to give us the instantaneous rate of change. Rather, a secant line gives you an average rate of change. So clearly, secant line is not what we want. But it forms a good basis for what we are looking for and satisfying a goal. Let's take 2 points, A, B. I'll call this x1, y1, x2, y2. I have 2 points, then I should be able to find its slope of that line. Do we remember that formula?
y2 minus y1 over x2.
Y2 minus y1 divided by x2 minus x1. So the slope great. Guess I'll get some numbers to. Are we clear with this rise over run? We've seen this lots of times. If I have to find the slope, every single point on the line, forget about the curve for a minute, just on the line, will that slope change?
Well, inside of it's fairly curious, but however, if we're just talking about straight line now.
We're going to ignore the curve for a minute, forget about the curve, just the blue line, and if I took every single point on that line, would the slope change? No, the slope of the line is constant, it'll be the same. But the objective is we want to find instantaneous rate of change for the curve. If I pick 2 points, let's see if I can. 1, 3, and 2. Good enough, just an example. Putting some meaning to x1, y1, and x2, y2. So going to call x1, y1, 1,3, right over there. X2, y2, 2,4, right over there. if I want to find the slope, I'll just plug it in the formula 4 minus 3 divided by 2 minus 1, 1 over 1, the slope is 1. Yes, we have a positive slope. A positive slope would imply that the line is increasing. Do we agree? And by the looks of it, the line is increasing. The purpose of finding the slope at a single point is to understand the behavior of this curve at any given instant. That's why we say instantaneous rate of change. Well, did it capture the behavior of this curve between the points A and B properly? Did the blue line capture the behavior of that curve between A and B? In the sense, the secant line is telling us that it's increasing. You say no, why? What do you think?
It decreases like in the minute.
Right, good. So on the interval A, B, sure, it is increasing for a bit, but then there is a part where it is decreasing. Naturally, using a secant line is not a good idea to understand the behavior of this curve, because you're going to miss out a whole lot of detail. Are you with me? So instead of a secant line, if I could come up with a way where I could find slopes at every given point, then I would understand the behavior of the curve properly. Good. Okay. Now you may ask, well, who cares about velocity at every single point? Well, good example, we want to study planets, satellites, all kinds of things, and they have to be done at a very, short interval, and that's where derivatives come into play. Good so far? Okay. How do we get to that tangent line, excuse me, that instantaneous rate of change?
Are you using tangential?
Exactly. So now that you've brought it up, what is a tangent line?
Still trying to figure out the definition, I apologize, but I do know generally at the very least, it's kind of like a secant line, but generally based on. It's kind of like a secant line, I apologize. for-
Kind of like a secant line, okay?
Would it be like a secant line of 2 points that are extremely close together?
That's a good way of putting it in a very practical sense, that is correct. So what you Tiffany says, well, it would be a secant line that goes through 2 points that are extremely close to each other. It might be quite difficult to see it. For one, I can't write, 2 points really close to each other. So the theoretical approach is to move this line, up that way. And eventually, it is going to touch 1 point. Do you agree?
Yep.
Let's say that point is right over there.
Also, what we.
So the line that touches a curve
The whole thing about tangent is, for instance, we're talking about geometry, tangent only.
So any line that touches a curve at exactly 1 point is called a tangent line. Now we all know that it really existed. If you have a line, the slope is the same no matter where you put that point. That would apply to the tangent line also. Do we agree? So the slope is going to be the same. But the slope that is of importance to us is right over there. Because we're trying to understand the behavior of that curve. So the only one point that I care about is the point where the line touches that curve. Yes. At the very edge, in that tiny little space, would you agree that green curve is increasing? Yes. So if I found the slope at that position, I am going to get a positive slope. Good. Now, would that positive slope be big or small? Huh? Small. Why? It's about to go down. It's about to make that turn. So right here, it's a very small change. Albeit it's a positive change. Do we agree? So what did the secant line give us? If I drew, say hundreds of tangent lines over there, each of them would give us a slope, correct? So I would have more of positive, few of negative. With me? If I have more positive numbers than negative numbers, if I add them together, the resulting answer would it be positive or negative? It has to be positive. The average will be positive. That's why we get this one. Does that make sense? More of positive, less of negative. It's one way of looking at it. So the secant line is giving you the average rate of change, hence the name average rate of change. On an interval, we're taking all the rates of changes and rates of change and averaging it to find that value. With me so far? And the tangent line is going to give that value at a single point. Tiffany said, we've got to get closer and closer and closer to that one point. That concept is very important just to understand the theoretical part of calculus. After that, it's just like algebra. You know the method, the mechanics, you can do the problem. Good. Yes. The problem is that we have time tape, and these are the times that we've recorded. So we had an initial time, and 36 minutes after the initial time, we've recorded heartbeats, and that's a cumulative value, and then 38, and then 40, 42, and 44. Naturally, if you're cumulatively adding heartbeats per person, do you expect it to increase or decrease? It better increase, or else the person died. So it has to be monotonically increasing. So clearly it is increasing. Now we want to use the slope of a secant line to estimate the slope exactly at 42 minutes. How do we find the slope of the secant line? Well, we need 2 points, x and y, and then we simply find the slope. I want you to pick the calculator, pick your calculator, and graph this. I can do this manually here. So we are going to pick that point, x1, y1, that point, x2, y2. Does it connect 2 points? Does it go through 2 points? Yes. So whatever I find would be the slope of the secant line. Good. Okay. Formula is easy. So y2, 2661 minus 2530 divided by 38 minus 36. And what do we get?
Effectively, what this is doing is trying to see.
Right, the x2 y2 has to be right here. x2 y2 So average. What do we have up there? 2948. And if we divide, what do we get?
69.6.
69 point.
Oh, wait, no.
No, what did it
never mind,
be?
never mind.
2948 minus
That's wrong.
Yeah, I was gonna say 61. We flopped them.
So I flopped them.
Yeah,
And then the bottom would be
Yeah, it's
42 minus 36.
3, 0. Thank you. 42 minus 30.
So what did those two still flip? 2948 minus 2530. Yeah.
Even if it's negative, we can put positive, but my bad. Is it all okay now? I think so. We're still doing 42 and 38. It is going to 2 points. So the next case would be 2948 minus 2661 divided by 42 minus 38. And what is that value? $71.75. Okay. The next one. 2948 minus the heartbeat at 40, 2806 divided by 42 minus 40. What do we get?
71.
Exactly.
Yeah.
71. And lastly, we have 42, 44. What is it? 40 and 44.
42, 44.
42 and 44. So 3080 minus 2948 divided by 44 minus 42. I'm switching the order so that I have the bigger number first. But I'm considering this to be y2 minus, excuse me, x2 minus x1, y2 minus x1. What is that last value?
66.
66, okay. So the problem wants to know as to what is happening to the heartbeat to get closer and closer to 42 or at 42 minutes. Yes. So that's pretty much what we're doing. If you look at how we moved prior to the mistake that I made, 42 is right here, correct? We started at 36, and we are getting closer and closer to 42. So 36 to 42, 38 to 42, 40 to 42. I've got pretty close to 42, right? And an approximate for that instantaneous rate of change at 42 would be about 71 beats. Because as you get closer and closer to 42, the value gets closer and closer to 71, and then it sort of makes a turn, right? So the rate of change in heartbeat is about, 71. If I took the average of all those values, go ahead and take the average of all those values.
88.15.
I have
Hey,
69.58.
69.58. If all the numbers are between 66 and
Yeah, like that.
69, yeah, how could you get 88? That's how we kill people in medicine. Write it the wrong way. And then get sued. So, the average rate of change from here to there is 69.58 beats. So that's how the heartbeat changes per minute. That sort of makes sense, right? 72 beats per minute. Yet we do not get an accurate value. As you can see, it's sort of changed, even though it seems like a straight line. Do you agree? So there are fluctuations at each point. Naked eye is not able to see that change. But in terms of the data, the line is kind of, slightly off here and there, but we're just not able to see it. But we know at 42, the rate of change is about 7 to 1, because as we got closer and closer to 42, it approached 7 to 1. Does that make sense? This is what Tiffany was talking about, getting closer and closer and coming to a small interval. Well, we got 40 to 42. Here is my question. Is that small enough to get an accurate value at 42? No, right? If I want an accurate value at 42, I better be extremely close to 42. I'm not yet. So this is just an approximate, it's all right, but it's not accurate. Does that make sense?
1.9 and then.
Okay.